Learning Outcome 7.5. Sketch the impulse response for zero-order hold and first-order hold reconstruction filters. We've been talking in previous learning outcomes about the signal and spectrum in the frequency domain, and how from the frequency domain perspective we can apply a filter and therefore reconstruct our original signal. We began the chapter talking about sampling from the time domain perspective, and how when we do sampling, we're looking at the values of our signal every t units, and from there we have a sampled time spectrum, which is our infinite pulse train, but now the area of each impulse is the amplitude of our time signal at those sampled time values. We're now going to look at this time signal, and from the time domain perspective, consider how can we reconstruct our original time signal. So the problem we have is we have original time signal, we've done sampling, we have this, and this is what corresponded to that spectrum we talked about before. But now, what can we apply to this, thinking about it from the time domain perspective, to get an x of t here that is either identical to or closely approximates this original signal x of t? So let's look at the sampled time signal a little bit more closely. Each of these impulses has an area related to our original signal x of t. And we'd like to find a way of taking these points and from them returning to this continuous value. One way to approach this is to take each of these samples and just hold the value for t units of time. And from there, we get an approximation of our signal, a stair-step approximation. This is what we call a sample and hold reconstruction. It works pretty well, and if capital T is smaller, therefore omega s is larger, which would then also mean that your spectrum has more gaps between it, then this would be a pretty good approximation because these bands would be very narrow. So let's look at this. How do we do this? To think about how to do it, let's look at one impulse alone for a moment. Given a single impulse, we want to create this rectangular pulse. It's going to go from 0 to t, assuming that this impulse is occurring at time 0. And this impulse would have an area, x of 0, our original time signal x at time 0, because our xp of t is the sum of our x at each of the sample times times an impulse at that sample time. So if this is what we have, let's say that x0 is 1. If we have an impulse that we apply through a filter to produce a square pulse, what must this filter be? We're trying to put every impulse through a filter, and by linearity, the scale value will transfer. By time shift, we can do this at any time. So we can consider the problem, thinking about it, if we put a single impulse into some filter, we want to get a square pulse out. So what must this filter be to produce this sort of response to an impulse? Please pause the video and think about this. I know you can keep the video going and just fast forward through here, but I really want you to take the time to pause the video and write some things out. Think about it. If you need a hint, review the sifting theorem video. Our input, convolved with our response, will give us this. Our input is delta of t, convolved with this unknown filter, should give us this. Therefore, what should this filter be? Review sifting theorem. Well, I hope you came up with a guess and you didn't just forward the video. Our H0 of t is also going to be a square pulse because convolution is the identity operator and it's going to have an amplitude of 1. So let's think about this. Can we do better than that? Zero order hold works pretty well. This is called a zero order hold filter. We use the number 0 to indicate that, and it's 0 because if we think about an equation which is of order 0, that means it's a constant, and this filter is a piecewise constant function. Can we do better than this? We really want to get to this, and we weren't quite there. What if we played connect the dot, where we want to draw something going from this point to this point to this point to this point in order to approximate it? I think it would be a better approximation. So now comes the question, what do we need to have as our filter to do this? Again, look at a single impulse. Well, right around there, if we just take it from face value, we need something which is going to give us this sort of response. But that's assuming we have these neighboring points. What if we only had one non-zero point, where all these light gray ones were 0? Redraw this on your paper with these gray ones set down to 0. And where would the connect the dots be then? And then follow a similar procedure to the zero order hold case. Here's a hint. If everything else was 0, playing connect the dots is going to be 0, 0, 0, 0, 0, our amplitude, 0, and a whole bunch more zeros. Here's the problem we're trying to work. Again, we can consider the case where our signal at time 0 happens to have an amplitude of 0. So we've got delta of t. We want to put it through some sort of filter. We want to go from time negative t through 0 to t, going from an amplitude of 0 to 1 to 0. This is our desired output. Again, sifting theorem, an impulse as an identity function. What do you think is h1? I hope you came up with this. Well, that doesn't look quite right. How does that all fit together? Let's consider each of these impulses. Around this particular impulse, when we do our convolution, linearity is then going to give us this as an amplitude for our triangle. When we take just this one, because we can add them separately by linearity, the area, the scaling factor for this impulse, is then going to form a scaling value on this triangle. Likewise, for each of the next one, the scaling value on each impulse, which is the amplitude for xp of t at that time point, will then scale our triangles. Now we have to go and add them. All that graphical addition I've been having you use, you have to use that here too. So here we have an amplitude of our xp at this time, and we're adding to it 0. So we're going to have this value. Here, this triangle gives you 0 input, this triangle gives you 0 input, and we're going to have the amplitude of the triangle at this time value. Between those 2 points, we have linear plus linear, so we can play connect the dots from here to here. Likewise here, this triangle gives an input of 0, this triangle gives an input of 0. We only have the contribution from this triangle. In between there, we're going to have linear plus linear, so we play connect the dots. And that whole idea of playing connect the dots is what we're working on. And we wind up with connecting the dots, and we get a good approximation of our original signal, x of t. So for zero order hold, we had a flat response, a constant response, a zero order response. For a first order hold, we have two linear equations working together. What's going to happen if we were to try and make an even better approximation with second order hold? Hint, this is piecewise zero order. This is piecewise first order. What do you think you're going to get here? It's going to be piecewise second order. We're going to have a second order parabola here, a second order parabola here, and a second order parabola here, which is really going to start halfway between these 2 points and end halfway between these 2 points, being 0 beyond there. So it's piecewise parabolic, piecewise second order. Okay, well, there's a number of issues that go along with this we really need to think about. So what do you think is going to happen if we were to continue from zero order, first order, second order? We could go to third order. That would be a cubic spline. Fourth order would be a fourth order spline. Fifth order. What do you think is going to be happening to the quality of our response, the quality of our reconstruction, as our order goes up to infinity? Yes, it's going to keep getting better. And we can do this. But infinity is really hard for us to implement, so we're probably not going to go there. But you need to think about it as the fact that it can happen. Okay, let's think about some more things. Is h0 of t causal? This is an impulse response. Chapter 2. How do we determine whether a system is causal given an impulse response in Chapter 2? We're looking to see whether our impulse response is 0 for all time t less than 0. Well, look, here we got a whole bunch of 0, so this is causal. Is h1 of t causal? Same definition of causality, Chapter 2. Is h1 of t equal to 0 for all t less than 0? Nope, this right here is non-zero for t between negative capital T and 0, so this is not causal. Well, we can only implement causal systems. As humans, we don't have the ability to build a system that can predict the future. We can only physically build causal systems. If we could build a system that could predict the future, you'd be making an awful lot of money, enough to certainly pay for your college education and then some. So what can we do? Because we as engineers want to solve this problem. The solution is just to change our time units. And now our triangle will start at 0. Well, is this causal? H of t is 0 for all t less than 0. What effect does this have on our response? We're no longer putting the triangle around the impulse, we're putting it next to the impulse. We're going to keep the area associated with the impulse. But because of time invariance, it just means that our response will be shifted t units in time. This isn't terrible. It just means we're going to get our exact signal back, but our signal will be shifted in time by capital T units. Since capital T quite often is milliseconds, can you wait for your recording off your iPhone another 1 millisecond, half a millisecond, 3 milliseconds in order to hear it? I bet you can. And you wouldn't even notice the difference. You'd think it was caused by something else. So in practice, that's what we do. Instead of using the impulse response h1 that's centered around 0, we shift it, and we accept that as engineers, our response will look the same, but be shifted in time. Well, what are we going to have to do here? Now we have to shift it by 2 t units, or at least 3/2 t units, in order to get this to be causal. We can do that. But if we were to continue trying to get a better approximation, we went from H0 to H1 to H2 to H3, we have to wait 2 t units. H4 is going to have to wait 5/2 t units. H5 is going to have to wait 3 t units. How long are we going to have to wait as our precision increases because our order is going to infinity? Ultimately, this is going to be infinitely wide. We don't want to wait that long. That's okay. We don't need to have that good of precision. You won't hear the difference when your digital audio is turned back into analog for you to listen to it. But you do need to think about these engineering considerations. Causality matters. And now you understand causality from your previous work in this course. We're now applying it here to a problem. And you understand the implications of what you need to do to get a better approximation. It's going to be more complicated to physically implement this, building a computer chip to do this, but you can do it. And there's more of a time delay, but you can do that. And then there's a trade-off, the quality of how good our reconstruction is, and then how much we have to wait. Looking at things in the frequency domain looked pretty simple, but then you need to leave a bigger gap between your spectra, meaning your sampling rate has to be higher, omega s needs to be larger, and we don't have ideal filters, so there's going to be some loss there too. These do work in practice. And zero order hold is actually quite often used because it's so easy to implement. Think about these concepts. Now I want to look at these again from the frequency perspective. We have our zero order hold filter. What is the Fourier transform of that? Please look in table 4.2, property number 8. You need to time shift it, which you can do from table 4.1, second property, time shifting. But if you look at transform number 8 in table 4.2, what do you get? Your good old sinc function. Review the video on the sinc function if you're not familiar with it. You need to know what this is. You need to have its picture in your mind. Okay, what about a triangular pulse? If we have a first order hold filter, what's the Fourier transform of that? Pause the video, think about it. As a hint, you can create a triangle in time by convolving two square pulses. You need to choose the appropriate widths, the appropriate heights, but just in general, square pulses, rectangular pulses. What's the Fourier transform of a square pulse? If we have convolution in time, what do we have in frequency? We're going to have a sinc times a sinc, or a sinc squared. Everything that's negative is going to be multiplied by something else that's negative. Negative times negative is positive. These values here are less than 1. If you have something less than 1 and you square it, does it get bigger or smaller? It gets smaller. So these lumps are going to get smaller. And that's our sinc squared function. Notice that both a sinc function and a sinc squared function are both low-pass filters. That's just what we used in the video for learning outcome 7.4, a low-pass filter when we thought about things in the frequency domain. So building a zero-order hold or a first-order hold, both are implementations of low-pass filters. What about a second-order hold? Same idea. Note that this one's going to go slightly negative because we have negative times negative times negative. So this one will occasionally go negative. but we're getting better and better approximations. And our drop-off is getting steeper, and we have less outside of our desired frequency band. Again, we can keep doing this to higher orders and get really good approximations of a low-pass filter with very little out-of-band signal. There's a lot of concepts in here. Watch this video a couple more times. Make sure all the places where I asked you to calculate something, you can do it. See you in class.